Okay, I apologize for that last bit where it just got really awkward and I was just probably not being very concisely correct with what I was trying to say. This recording program is a little whack, so it caught me off guard. Just to get to the point, the two forces you need to know, diffusion and electricity. So diffusion, concentration gradient, electricity, charge gradient. Cool. So moving on from membrane potential and going on to action potential, please know the curve. I feel like everyone should know the curve by now. Know the different steps of an action potential and understand like what's going on. So very quickly going through it, there's the step one where there's a stimulus applied and it brings the charge that's initially negative to threshold, which is a little less negative. And once it hits that threshold, it's an all or nothing response. So you have depolarization and it shoots all the way up, hits a maximum point, and then it repolarizes to go down. And as it repolarizes, it hyperpolarizes before it eventually neutralizes out to go back to this resting membrane potential. So again, what that looks like in terms of the movement of ions is that you have enough sodium influx via that pump that we see from right here. And in that case, where there's enough, it hits this threshold and it depolarizes because of the influx of positive charge. And then as it becomes more and more positive, it hits a point where the sodium, the voltage gated sodium channel closes. And then at that point, you have the voltage gated potassium channel open, and then um, the outward movement of potassium, which is like the loss of this positive charge, it leaves uh, the intracellular section of the cell, and at that point you have repolarization. And so because there's so much of it leaking out, that's what causes hyperpolarization. And again, you want to have this refractory period so that you don't have another action potential firing immediately after. And then the other point I want to make is the difference between a graded potential and an action potential. You don't need to remember what a graded potential is, but basically what it is this example right here where there's a stimulus applied, but it's not enough. So all you see is a little burst right there. And then when you actually have enough, that's what fires the action potential. So graded potential is like a failed attempt at an action potential. You just have like little bursts depending on how much is applied, and eventually it'll hit enough to become that action potential. I already talked about myelination the last video. And then the last thing I want to remind you is about the channel blocking drugs. Remember TTX, tetrodotoxin, and lidocaine are sodium channel blockers. And then in the case of a potassium, she's probably going to tell you which channel it's going to block. So don't worry about memorizing any really, but if you were expected to, I would say no TTX and lidocaine, which are both sodium. And then, the last note I wanted to make again is again numbers. There's just so much discrepancy between like the values that are discussed in the scientific community. So just try to get around -70, -40 to -50 for the threshold, and then it should be +30, +40. I usually do -70, -40, and +40, but shouldn't be a problem for the final. Next up, we are moving on to synaptic transmission. We are really beating this to death, but electrical versus chemical. Electrical is faster, chemical is slower. And as Pei reiterated in lecture today, the signal of an action potential starts off as electrical, and then as it travels to the end of the presynaptic neuron and it moves to the postsynaptic neuron, that's chemical. And then after that, it goes back to being electrical because it starts all over again on another neuron. So electrical synapses are faster, they're bidirectional, and they're not selective about ions because it's really just all connected. So it's all voltage based or voltage powered. And then again, it becomes a chemical signal. Chemical synapses are slower and they depend on the release of neurotransmitters, which are chemical and they're specific. Okay, so based on the slide, you can read off what's going on, but very quickly, just remind you a few points that were made on the study guide that are not so quick to pick up from this diagram here. First off, you have the action potential traveling down this way, and that's down the presynaptic axon, and then it hits this terminal end. And what happens here is as it goes, that electrical synapse causes this conformational change where it opens this calcium channel, this voltage gated calcium channel, and then you have an influx of calcium which binds to the V snares. Remember, V is vesicle, so the V snares on the synaptic vesicles, and then that's what causes them to have another conformational change that allows them to bind with the T snares on this membrane. And then that's what causes the binding that leads to the fusion that opens up this vesicle and allows for the release of neurotransmitters. The neurotransmitters are then received by their respective receptors, and then these receptors will process it such that if it's excitatory, it will continue another action potential down the postsynaptic neuron. If it's inhibitory, then it stops right there. So that's a pretty important thing, a differentiation I wanted to make because I didn't make that earlier on. So another point that I want to make is vesicle recycling and reuptake. What happens if it doesn't work? So both the neurotransmitters that don't bind and the vesicles itself are recycled. You don't really need to know the full process of that other than just knowing that they're recycled. In the case that they're not recycled, you're going to run out. That's pretty straightforward. Yeah, so let's go ahead and move on to the next lecture slide. There's excitatory versus inhibitory, just as what I was talking about. I really think that she could ask you about this. She asked again in class today about the inhibitory synapse. It was on your midterm. Maybe next time it might be excitatory synapse. So again, with excitatory synapse, it's glutamate based. You only really need to know two neurotransmitters for a good chunk of this class, and it's glutamate and GABA. So what glutamate does is it opens the voltage gated sodium channels, and that allows for the influx of sodium. And then for GABA, what it does is it opens the GABA gated chlorine channels, and it hyperpolarizes. So when it hyperpolarizes, you can't, it's not, it's like the end point of the action potential. You need a lot more sodium in order to overcome that. And that's not really the case here. So that's how you end up kind of stopping a signal in a sense. So please remember the different ions involved and the different neurotransmitters. Okay, retrograde signaling. So retrograde signaling is very specific to GABA and endocannabinoids. So the process as follows is that you have the endocannabinoids that go from the postsynaptic end this time to the presynaptic end. They bind to the CB1 receptor, and then what it does is it suppresses the voltage-gated calcium channel, and once it suppresses that, you don't have that influx of calcium anymore, which means that you don't have it binding to the V snares, which then don't bind to V snares. So that prevents this whole fusion process, and if there's no fusion, there's no neurotransmitter release. And like I said, it's GABA specific. So if there's no GABA, which again, GABA is inhibitory, there's going to be less inhibition. So it will actually, in a sense, be excitatory. It's this feedback loop where you want it to keep going. You want it to not have so much inhibition. But the main takeaway from this is that you are able to send signals backwards. Like you're able to go from postsynaptic to presynaptic. Okay, and drugs, we kind of already went through this. Feel free to review the slide as needed. It's helpful to know what the graphs look like, which we went over already. So moving on to gustatory system. A few things I wanted to add on about the CRFI is that what happens is that they use this like machine to detect the brightness of neurons, and then the brighter it is, the more activity is going on, and the activity is measured by action potentials. And this is what they use to really understand the different firing pathways for not just the gustatory system, but also the olfactory system. Okay, I'm going to end this video here and start a new one.